All right, so this is March. Happy March. We're starting section 8.2 today. We'll discuss this again on Wednesday. This is lecture 19. Section 8.2 is about what are called series. All right. So I take a different approach than the book takes in this section. I don't like the book's approach. I feel like it's kind of confusing. I don't know if my approach is better. I just know that I don't like the book's approach. So this is my attempt. So bear with me. So meeting part 1. Recall sequences. This is sequences is section 8.1. So we discussed infinite sequences. So that's denoted by a symbol like this, a subscript n, curly brackets, n equals 1 to infinity. And what that stands for is this list, A1, comma, A2, comma, dot, 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 comma, A subscript n is a generic entry going on forever. The key thing about sequences is the things in this list are separated by commas. Now, we considered this limit as n goes to infinity of an. This limit may or may not exist. So it's just the limit of the things on the list. If the limit exists and is a real number, we say that the sequence converges and converges to that real number. So if the limit exists and is as a real number, then we say the sequence converges. Say the sequence converges to L. All right, now, part 2. Part 2 is about a sequence of partial sums. So, so we're going to consider adding together some of the terms of a sequence. So sum of the terms of a sequence. My niece had a baby, and when my phone blows up, it means that somebody has posted a cute picture of Connor of Cooper, and then the entire family is weighing in with loves and likes and whatnot. All right, so we're going to start by adding just the first k terms. Of a sequence A subscript n. So we've got a sequence. It's this thing where the items in the list are separated by commas. So here's a definition of partial sums. So here are the words. The kth partial sum of A subscript n. So here's the symbol. S subscript k. That's a k. Don't complain about my k's. And here's what it means. The number, so in other words, S subscript k apparently stands for a number, so I'm going to tell you what that number is. So the number is denoted by S subscript k, and what it is this. You take the terms in the sequence, A subscript n, and you add together the first k of them. So the summation symbol is used for that. We start with n equals 1, and we end with n equals k. So what that means is A1 plus A2 plus ending with A subscript k. Notice that the partial sum always exists. You've got a list of numbers, and you're adding together a finite bunch of numbers, so you're going to get a number. And notice that with S subscript k, there are plus signs in here. So the sequence had these terms with commas between them. The partial sum has some of these terms, but with plus signs in between them. So realize that this is S subscript k is a new sequence. So S subscript 1 is just A1, S subscript 2 is A1 plus A2, and so forth. End up with S subscript K is A1 plus A2 plus ... plus A to the K, ending there, and go on. Every one of the terms in this list is a number. And it's obtained by adding together a finite batch of numbers. This is called a sequence of partial sums. Now, this sequence of partial sums, of course, we're inquiring minds. So when we had a sequence before, in section 8.1, we often wanted to know if that sequence converges. Well, here we have a sequence. It's a sequence of partial sums, so we're going to want to know, it's interesting to know whether or not this sequence of partial sums converges. So the sequence SK may or may not converge. So that is the limit as k goes to infinity of s subscript k. So that's the limit as k goes to infinity of the sum n goes from 1 to k of an. This limit may or may not exist. And by saying the limit may or may not exist, we mean it may or may not exist as a real number. So that brings us to meeting part 3, which is infinite series. Or just simply series. So here's a definition. So here's the symbol. You have the summation symbol, and the index is n equals 1 all the way to infinity. And another symbol for this is this. A1 plus A2 plus so on, all the way up to AN plus, and you just keep going. So it's an infinite list of terms, but in between the terms are plus signs. So it's terms of the sequence AN, but with plus signs between them. Remember, the sequence AN was way over there, and it had the terms of the sequence with commas between them. The series, so the book doesn't really give this a name. Let's just make up a name. So the infinite series based on AN, on the sequence A subscript N. Again, the book doesn't really give this a name, but the chapter or the section of the book is called series. So this is a series. And what it means is, it means the limit. Or it's also spoken this way. The sum as n goes from 1 to infinity of AN. You can see where that came from. We're kind of adding these all up. Now the thing is, addition is a binary operation. You add two numbers together. You learned that in grade school. That's it. Addition is a binary operation. You can add up a bunch of numbers by doing them pairwise, but addition is a binary operation. There is no thing where we add together an infinite set of numbers. That's just not an operation. So this symbol looks impressive. You should show this to your parents. It'll really intimidate them. But the thing is, we can't add together an infinite set of things. So what this means is the limit. So in other words, this symbol stands for something that's a limit. So I'm going to write this down. This symbol, n equals 1 to infinity of AN, that means this. The limit as k goes to infinity of the kth partial sum. In other words, it's the limit as k goes to infinity of the sum as n goes from 1 to k of AN. So here's a list of, here's a sequence of partial sums. This is the list S subscript K. If this has a limit, this list, then the sequence, then that limit is what's called the series or the infinite sum, or the sum. I shouldn't say infinite sum. So if the sequence, if this sequence converges, then we say that this, so this limit exists. Then we say that this series converges. So if the limit as k goes to infinity of sk exists, we say the series converges to the number. So I should say that the limit is some number s, a real number. So then we say the series converges to S. So the series as n goes from 1 to infinity of AN is the limit as k goes to infinity of SK, and that's the number S. If the limit doesn't exist, we say that the series is divergent. Okay, so we've got sequences that are lists of items separated by commas. We have sequences of partial sums. That's just another sequence, S1, comma, S2, comma, and so forth. But each partial sum is made up by adding things together. And then we have a completely different thing, which is a series. So it looks like this, and it's a limit of a sequence of partial sums. Okay. So meeting part 4, which will take us to the rest of the hour, hopefully we'll get done. Meeting part 4 is about what's called the geometric sequence and the geometric series. So a geometric sequence is a sequence of the form, well, A subscript n equals r to the n minus 1 for n equals 1, 2, and so forth. Now the book puts a constant in front of this. I don't see the need for that. The constant you can deal with later. I just think of the geometric sequence as just these terms r, where r to some power, where r is a real number. So what does this look like? Well, when n is 1, I get r to the 0, so I get the number 1. When n is 2, I get r to the 2 minus 1, that's r. Then I get r squared, r cubed, up to the nth term is r to the n minus 1, and then I keep going. So there's the geometric sequence. It's a list of things separated by commas. So this sequence occurs all through the sciences. So again, the book calls the geometric sequence the same thing, but with a constant in front. There's just no need to complicate it that way. You can deal with the constant easy enough later. So behavior of the geometric sequence for various categories of R. That's what I want to do here. I want to make a great big table, make you feel like you're getting your money's worth. So category, and then an example of an R in that category, and then the geometric sequence. And then conclusion. About the geometric sequence. So I'm going to have 5 categories. So the first category is R less than -1. So an example of an R in that category could be R equals -2. And so the geometric sequence for that R would be 1, -2, 4, -8, and so forth. So who wants to make a conclusion about that geometric sequence? Does that geometric sequence converge or diverge? Kinsey? Diverges. I'd like to say it diverges to infinity, but it doesn't. Some of the numbers are getting huge and positive, some of them are getting huge and negative. It is an alternating sequence. Now another category is R equals -1. Of course, the only thing in that category is R equals -1. So the geometric sequence here is 1, -1, 1, -1, and so forth, as you raise -1 to higher and higher powers. So who wants to tell me about that sequence? Does it converge or diverge?
It oscillates.
Say it again?
Oscillates.
So does that mean it converges or diverges?
Diverges.
Diverges. So it oscillates between -1 and 1. Diverges. So oscillates. Oscillates is stronger than just saying it's alternating. It is alternating, but it's alternating in the terms don't change the size. It just keeps, it's like a pendulum between -1 and 1. Another category would be R between -1 and 1, strictly. So an example in that category would be R equals -1/2. So let's make the list of terms. It would be 1 -1/2 plus 1/4 -1/8, and so forth. Who wants to weigh in on this? Does this converge or diverge? If it converges, what does it converge to?
Converges to 0?
Yeah, converges to 0, because the terms are getting closer and closer to 0. It is alternating. The consecutive terms have opposite signs. So again, oscillating is a special kind of alternating where the terms don't get closer and closer to some number. Alternating, is a sequence can converge and be alternating. So our first example was alternating and diverges. This example was alternating and converges. This example is alternating but diverges because it's oscillating. Okay, another category is R equals 1. So of course the only representative there is the number 1. So there's the sequence. Somebody who's wearing green, does that sequence converge or diverge? Converges to, good, converges to 1. So notice, the geometric, oh, let's go on. My final category is r greater than 1. So an example here would be r equals 2. So then the terms are 1, 2, 4, 8. Somebody wearing blue, raise your hand if you can tell me whether this series converges or diverges. Jace?
Diverges.
Okay, this is good. So it diverges. And I can say it diverges to infinity. I couldn't say that about this one, because this sequence was, the terms are getting bigger and bigger, but they were alternating sign. So notice, among the geometric sequences, only 2 categories converge. One big category converges to 0. One category with just a single sequence in it converges to the number 1. But all other geometric sequences diverge. Now, consider the sequence of partial sums. Remember what that is. SK is this. We add up the first terms, so A1 to AK, but for the geometric sequence, that means that we do 1 plus R plus, and we end with R to the K minus 1. Okay, well, we can figure out a formula for SK. So notice that if I take SK and I multiply it by R, that means that I multiply every one of those terms by R. So that's going to become an R, and that's going to become an R squared, and that's going to become, well, R to the K. Now, just before that, there's an R to the K minus 1. So maybe I should have done that up here. So this sequence ends with R to the K minus 2 plus R to the K. The last term in that kth partial sum is adding on the R to the K minus 1 power. Sorry, K minus 1 power. That's the AK term. Sorry to change this. So that's how that sequence of partial sums, that's how the partial sum SK looks. And if I hit everything in that list with an R, and multiply everything in that list by R, I get this sum. So if I compute SK minus RSK, look what happens. I have to take this list and subtract this list. So I get 1 plus R plus all the way up to R to the K minus 1, K minus 2 plus R to the K minus 1. That's that whole list. And I'm going to subtract this whole list, R plus all the way up to R to the K minus 1 plus R to the K. So when I subtract that bottom list from the top list, notice a bunch of terms cancel. I'm going to get my red chalk. So this term cancels that term. This term cancels this term. And all these terms in the middle cancel each other. And I end up with 1 minus r to the k. And so that's the right side. Now on the left side, let's factor out s subscript k. If I do that, I get 1 minus r times s subscript k on the left side. Now, if r is not the number 1, so whenever r is not the number 1, we know that 1 minus r is not the number 0. So we can divide both sides by 1 minus r. And we get this formula. S subscript k equals 1 minus r to the k divided by 1 minus r. So this is a really cool formula. How about this? I'm sorry. Let's find the value of that sum. Notice this is R, or geometric sequence, this is a partial sum of a geometric sequence. With, well, what's the value of R for this geometric sequence? R is the number 2/3. And what is, which partial sum is this? Well, that's r to the 0, r to the 1, r squared, r cubed, r to the 4th. And so we have k equals 4. So that sum the sum would be 1 minus r to the k, so it's going to be 2/3 to the 4th divided by 1 minus 2/3. So that would be 1 minus 16 over 81 divided by 1 minus 2/3. So let's see, 1 minus 16 over 81, that's 81 minus 16 all over 81. So that's going to be 65 over 81 divided by 1 minus 2/3 is 1/3. But dividing by 1/3 is the same as multiplying by 3. So 3 times 65 over 81. Now here's where most students, like 99% of students, will multiply 3 times 65 with great work, and then they'll divide by 81, but cancel before multiplying. So this is 65 over 27. There you go. That's the value of this sum. All right, can I erase this because I want to use this space? Everybody got this? If not, you can see the video at next year's Academy Awards. So what I want to do is I want to observe the behavior of this sequence. So behavior of the sequence of partial sums. Behavior of sequence of partial sums of the geometric sequence. So again, over there, we have the geometric sequence. All the items had commas between them. We are looking at behavior of the geometric sequence. Now we're going to have those same categories. Category example R, the sequence of partial sums. And then I want to talk about the conclusion. About a conclusion about the sequence of partial sums. So I have those same 5 categories. So the first category was R is less than -1. So an example was R equals -2. And the sequence of partial sums would be SK would be 1 minus 2 plus 4 minus 8 plus, we go all the way up to 2 raised to the k minus 1. Because the k, remember the terms in that geometric sequence, a subscript n is r to the n minus 1, a subscript k is r to the k minus 1. So this term, this partial sum ends with that term. And I've got to move, after taking all the time to write that, I want to write down what we know about this formula. Yeah? Yeah, -2. And we know what this equals. This is 1 minus a minus 2 to the k over 1 minus a minus 2. So that's 1 minus a minus 2 to the k all over 3. So who wants to weigh in? Does this sequence of partial sums converge or diverge? So again, this describes a list of numbers. And the items on that list look like this. They're each a finite sum. And here's the values. Does that list converge or diverge? Diverges. Right, diverges. Because when k gets bigger and bigger, I'm raising -2 to bigger and bigger powers. It's swinging back and forth between huge positive numbers, huge negative numbers. So this value doesn't settle down. What about when r equals -1? So that's the only representative. So SK is going to be 1 minus 1 plus 1 minus 1 plus all the way up to -1 to the k minus 1. Now we know a value for that. That's 1 minus a minus 1 to the k, all divided by 1 minus a minus 1. So in other words, 1 minus a minus 1 to the k, all over 2. Does this sequence converge or diverge? Got one hand up. I'd like to get some more hands going here. Yes?
Diverges?
Diverges. Go back over here. The geometric sequence with r equals -1 oscillates between -1 and 1. This list of numbers alternating between -1 and 1. Look at this list of numbers. This is going to oscillate too, but what's it going to oscillate between? Well, when k is an even number, that's going to be 1 minus 1. That's going to be 0. When k is an odd number, this is going to be 1 minus minus 1. It's going to be 2. So it oscillates between 0 and 1. It doesn't oscillate between -1 and 1. It oscillates, this sequence of partial sums diverges because it oscillates between 0 and 1. And then we have that big category of r's between -1 and 1 with an example of r being -1/2. And so the sequence of partial sums would look like this. 1 minus 1/2 plus 1/4 minus 1/8 plus go all the way up to -1/2 to the k minus 1, which may be a positive number or a minus number depending on whether k is an even or odd. And the value of that is 1 minus a minus 1/2 to the k over 1 minus a minus 1/2. Well, 1 minus a minus 1/2 is 3/2. So there's a 3/2 in the bottom, and at the top I have 1 minus a minus 1/2 to the k power. Does that sequence converge or diverge? Andrew, you're quiet today. What do you think? Does this sequence converge or diverge?
Looks like it diverges.
Why? When k gets bigger and bigger and bigger, what's happening to -1/2 to the k?
I'm sorry, I was kind of zoned out.
Okay, that's why I brought you back. So does this list, this describes the items in the sequence of partial sums. Does that sequence converge or diverge as k goes to infinity?
So the -1/2 to the k is going to be approaching 0, right?
Right.
So it's approaching 1 over √2, so it's approaching 2/3.
Exactly. So converges to, that term is going to become 0 in the limit. So 1 over 1 minus a minus 1/2. So that's 1 over 3/2. So as Andrew said, it converges to 2/3. Isn't that cool? How about when r equals 1? Well, then the kth partial sum is 1 plus 1 plus 1. I have k of these terms. What's the value of that? Remember, this formula, we derived this formula in the special case where r was not equal to 1. This formula would not give us a value when r equals 1 because we'd be dividing by 0. But we don't need a stinking formula. What's the value of this? 1 plus 1 plus 1 k times. Exactly. So the kth term in this sequence has value k. So does the sequence converge or diverge as k gets bigger and bigger? Sequence goes to infinity. Another category, the final category, was r greater than 1. So an example was r equals 2. So sk would be 1 plus 2 plus 4 plus 8, all the way up to 2 to the k minus 1. And the value of that would be 1 minus 2 to the k over 1 minus 2. Now that's 1 minus 2 to the k over minus 1. So I can just multiply top and bottom by minus 1, and I get 2 to the k minus 1. So what's your conclusion about that sequence? Does that sequence converge or diverge? Marcy?
Diverges to infinity.
Yeah, diverges to infinity. Okay, so we have the geometric sequence over there, which converges in just two categories. Converges when r is between -1 and 1, and also converges when r is equal to 1. But then we have the associated list of the associated sequence of partial sums, and it always diverges, except in the one case when r is between -1 and 1. All right, so we have just 5 more minutes. So we're still talking about geometric sequences, sequences of geometric sums of geometric sequences. Sequences of partial sums of geometric sequences. That's over there on the right. And so finally going to talk about geometric series. So definition of geometric series. So here's the symbol, or the words. Geometric series with ratio r. Here's the meaning. This should say ratio r. Here's the meaning. Or here's the symbol. We do the symbol, the sum as from n goes from 1 to infinity of r to the n minus 1. And this is the meaning. This symbol, remember, the sum as n goes, or I'm not sure if this is, remember, I guess we haven't talked about this before. This symbol is the limit. So this symbol, the sum as n goes from 1 to infinity of r to the n minus 1, is going to be defined to be this limit as k goes to infinity of the kth partial sum. So that's the limit as k goes to infinity of the sum as n goes from 1 to k of r to the k minus 1, r to the n minus 1. So we've seen that this series converges when r is between -1 and 1. When r is between -1 and 1, this series converges to, well, this number that we can call s. That's the limit as k goes to infinity of sk. So that's the limit as k goes to infinity of 1 minus r to the k over 1 minus r. And when r is between -1 and 1, this term gets smaller and smaller and smaller when k gets bigger and bigger. So it just converges, series converges to 1 over 1 minus r. Otherwise, the series diverges. So when R is not between -1 and 1, the series diverges. So the last thing I want to do is 2 quick examples. Two series which converges. So series A is the sum as n goes from 1 to infinity of e to the n over 3 to the n minus 1. And over here, series B is the sum as n goes from 1 to infinity of 3 to the n over e to the n minus 1. So one of these converges and one of these diverges. Well, let's get this in the form that's more familiar. We want to get it in the form of some number r raised to the n minus 1 power. So let's break off a factor of e. So we have e times e to the n minus 1 over r to the n minus 1. Now the book doesn't do this, but we can do that. Well, this is coming. I'm going to go ahead and talk about it now. I think you can believe me that we can pull that e outside.
Should that R be a 3?
3. Thank you. And inside I have e over 3 to the n minus 1. Over on this side, I can pull out a factor of 3. So I have 3 times 3 to the n minus 1 over e to the n minus 1. I can pull the 3 outside. So which of these series converges? Series A or series B? Got 3 hands up. Let's get some more hands up. What do you say?
A.
A. You're correct. Why?
Because R is less than 1.
Exactly. E over 3 is less than 1. It's greater than 0. Remember, E is a number between 2 and 3. So this series converges. So the series converges to 1 over 1 minus e over 3. So the sum is that with an e in front. E times e over 1 minus e over 3. This series has r is greater than 1. 3 over e is greater than 1, so this diverges. Great, thank you, Gabriel. Let me quickly see if did anybody else come in.